Welcome, Physics 181, to our first topic in thermodynamics, temperature and heat. This is mostly stuff out of Chapter 1 in the textbook. But temperature and heat, that's the stuff we want to talk about, sort of the differences between these two ideas. They are different things. The first thing we want to do is to define the zeroth law of thermodynamics. It's called the zeroth law because the first law had been around and been called the first law for a long time before scientists realized that we really needed this one to justify our definition of the first one. So what comes before 1? 0. Now we're now to the zeroth law. And it says something like this. If I have two objects, these blocks B and C, and they're in thermal equilibrium, meaning there's no exchange of heat energy between the two, then and then I bring in my thermometer, another object, and I put it into thermal equilibrium with B. That's kind of how thermometers work. It comes into thermal equilibrium, whatever measuring device, it'll come into thermal equilibrium with whatever you're trying to measure the temperature of, most of these thermometers. And then then I get A and B in thermal equilibrium. And the zeroth law says if B and C are in thermal equilibrium, and then A is in equilibrium with B, then A has to also be in equilibrium with C. So like this is what the textbook says exactly. If objects A and B are separately in thermal equilibrium with a third object C, then A and B are in thermal equilibrium with each other. Really, things at the same temperature are in thermal equilibrium. But what does temperature really mean? Let's talk about it briefly. Macroscopically, it's a property of a material or a system that determines whether things are in thermal equilibrium, right, with other objects or other systems. If two objects have different temperatures, they're not in thermal equilibrium, and there'll probably be some energy exchange, spontaneous, as it turns out, that just happens. The thing with more energy that's at higher temperature will give energy to the thing at lower temperature. Microscopically, and this is probably, I think, the more revealing definition, a measure of the average motion of the molecules that make up any substance. So everything is kind of jiggling around a little bit, right? Even solids that look like they're not moving internally, the atoms and molecules that make that up are moving around, right? How much they move on average, because this one right here might be, might have one here moving pretty fast, and the one next to it doesn't move quite as fast. But you average out all the molecules' speeds, really. And we'll get to a more quantitative definition in this when we talk about the kinetic theory of gases. That leads us to a more quantitative definition of how average motion leads to temperature. But for now, keep that in mind. Average motion of molecules leads to temperature. We use thermometers to measure temperature. They're always based on some physical property of a system, right? By far the most common is the volume of a liquid. When people think, oh, what's a thermometer? Everybody thinks that stick with some red fluid in it. That's usually alcohol with some red dye in it. Probably actually the most common thing used to measure is the electrical resistance of a conductor or a semiconductor that varies with temperature. That's probably, in our modern age, the most commonly used temperature measuring device. They're all over the place. But even things like the color of an object, we'll see that when we look at heat transfer things, radiation, and this is color used in a very broad definition that only physicists would use, meaning the brightest emitted wavelength from a glowing object, glowing in whatever range of the electromagnetic spectrum. Physicists are different than artists. We would say that there's some maybe color in air quotes associated with radio waves. We just call it wavelength for radio waves, or maybe frequency for radio waves. But a temperature scale can be established on the basis of any of these properties. And I'm sure you've heard of a few. In the United States, colloquially, we always use the Fahrenheit temperature scale for reporting temperatures inside and outside. That's arguably a pretty good one for inside-outside temperatures because it's pretty broad. 0 degrees Fahrenheit, that's really cold, right? Well below the freezing point of water. 100 degrees Fahrenheit, pretty hot, but well below the the boiling point of water. From 0 to 100 in Celsius, that's water is coexisting with ice, the freezing point. 100 is water coexisting with water vapor, steam, the boiling point, right? At least at sea level pressures, standard pressure. But they're just different stories. Celsius used water, something he thought other people can easily access this material, and they can perform the same. They can calibrate to my temperature scale easily. That was probably a good thing. Fahrenheit was a little weird. I think Fahrenheit would make a great Halloween costume because this is kind of a creepy story. Fahrenheit was a nobleman in Poland, Germany area in his time. I don't know what country it falls in now, but I think he was Polish. I could be mistaken. But anyway, Fahrenheit was a nobleman, and he owned lands and cattle and a few other, and he wanted to establish his own temperature scale. So he had kind of the alcohol thermometer, like most of them did, or maybe a mercury thermometer, some volume of a liquid thermometer. And what he did is he just established 0 as the coldest temperature he measured outside in the wintertime. So like the shortest column of fluid, right? He wanted to make the 100-degree mark human body temperature. But in order to do that, you'd have to go jamming this like inside, inside a bunch of people. He wasn't quite that crazy. He probably thought about it, but thought, nah, I'll probably, at the time, get thrown in jail for that, right? Best case scenario. So he thought, what else do I have? Well, I own a bunch of cattle. As the cattle go to the slaughterhouse, they would drain blood out of the cattle as they slaughtered them, right? And so what he did is these freshly slaughtered cattle, he would go and get a bowl full of right out of the cow, warm cow blood, and stick his thermometer in it. And he marked that as 100 degrees. Creepy, right? The creepy story of Fahrenheit. There you go. But of course, those are the scales that we're comfortable with. Or Fahrenheit is what most people in the US are comfortable with. I kind of prefer Celsius just because everybody else uses that around the world. There are only something like 3 countries that really still measure things in Fahrenheit. It's used colloquially a few places, but Celsius is probably more appropriate. If I were in charge, it'd probably be Kelvin, but nobody wants to go, man, it's warm outside. It's like 310. So I can give it up, right? The Kelvin is the official SI unit. If you want to be sure that your calculations in thermodynamics are going to be correct, put all the temperatures in Kelvin. If we're looking at temperature differences, using Celsius degrees is okay because the difference in 1 degree Celsius is exactly the same as the difference in 1 Kelvin. Notice I didn't say degrees Kelvin. It's just Kelvin. It's a unit of measure. Degree is another weird thing. But here's the thing. Remember that temperature is a measure of average motion of molecules? Well, Kelvin is an absolute temperature scale, ultimately defined based on this Boltzmann constant. You're going to want that Boltzmann constant later. It's an agreed upon exact value now in the SI system. But the 0 point is really set as 0 molecular motion. That means you can't really measure it. Any of those thermometer systems, if I tried to measure 0, I would disturb the molecules in a system in the process of taking the measurement, right? So that becomes pretty difficult. That said, the record lab temperature is on the scale of a couple of 1 or 2 nanokelvin, billionths of Kelvin. So we can get pretty close in extreme situations. But that 0 Kelvin, it's minus 273.15 Celsius, and that's the conversion between the two. If you have something in Celsius, subtract, you can add 273.15 and you get something in Kelvin. If you have something in Kelvin, you can subtract 273.15 and you get its temperature in Celsius, right? Absolute 0 in Fahrenheit is minus 459.67, something, close enough, right? About minus 460. So different, right? But take a look at those scales, know how to convert, particularly between Kelvin and Celsius. I'm not going to throw a lot of Fahrenheit at you. It's too creepy. Our next topic is not in our textbook, so use this as a resource. Use this video and these slides as a resource about Newton's law of cooling. We'll also cover this in the lab we'll do a quick experiment with Newton's law of cooling. And I think I have a Newton's law of cooling programming trinket exercise that you can look at as well to help you learn this stuff. But really, it kind of goes with the story of Newton developing some differential calculus. He said that a warm object of temperature T cooling off in a room or an environment, we'll call it the room for ease of language, with a temperature T sub R. So we look at that, if you look at that difference in temperature, the rate of change of the difference is equal to a constant times the difference. And that's it. So in nowadays, we write this as a differential equation, as shown here, right? What's the solution to this? He says the rate of change of the difference of temperature with respect to time equals minus some constant, because we know temperature is decreasing. The difference in temperature is getting smaller, minus some constant times the difference. Well, that's a differential equation. We as physicists might just say, yeah, I'll walk it over to the math department, go to lunch, come back, they'll solve it for me. Of course, we know enough math as physicists that we know the answer to this. And the way to think about this differential equation is to say the following. We're looking for a function for d such that when I take a derivative, I get minus a constant times whatever I had. What kind of function do you pretty much return the same function with maybe a constant in front of it when you take the derivative? Well, if we ask the math department or if we have some experience with these, we know, oh, that's the exponential function. And so to solve the differential equation, I make my guess, which turns out to be correct, right? I'm going to put in a constant d naught, an initial temperature difference, because I know I'm going to have some boundary condition in the parlance of differential equations that I need to meet, right? And then this constant k, let me make it capital K like we have. This is the cooling constant, right? And it's just some constant number in units of 1 over time. 1 over seconds if we're measuring time in seconds, 1 over minutes if we're measuring time in minutes, whatever, right? It's like a decay constant, but we call it the cooling constant since this is cooling. Notice, though, if I take a derivative of this with respect to time, you got to do, I don't know if it's a chain rule or product rule, or I think it's chain rule, but I have to take a derivative of the thing, the exponential. The end result is that this minus k pops down in front of everything. And I end up with minus k times the original function that I had before, just like I wanted to. I've checked. I posed an Ansatz, German for guessing, and proved that my guess works. So that's Newton's law of cooling, right there. T in time, this little t in time. D is the temperature difference. Remember that that's the temperature difference, not the temperature of any individual thing. So let's look at this quick example. I'm going to work through it to show you. 2 cups of water. One's at 30 degrees Celsius, one's at 40 degrees Celsius. They are in a room, identical room. Temperature is 23 Celsius. And the temperature of the room we're going to assume stays constant. It's so big that, having a warm cup of water and there's not going to change the temperature of the room. We say the rate depends on the system, right? But these are 2 cups of water. They're identical cups, and they're in the same room. So we're going to guess that they have the same cooling constant. We'll assume we know the cooling constant, 0.5 per second. I'm going to call the 30 degrees Celsius, let's call this temperature A, and this temperature B. And this would be temperature A naught and temperature B naught, the initial temperatures. Temperature room that we're going to need is at 23 degrees C, right? This allows us to calculate. Remember, the difference in temperature is temperature of the thing minus temperature of the room. We can quickly calculate difference A naught, the beginning temperature difference. That's 30 minus 23. That's 7, right? dB naught, 40 minus 23, 17, right? Now I can apply this thing to find after 1 second. I can find dA of t equals 1 second. That's going to be dA naught, the initial temperature difference, e to the minus k, which I know is 0.5, times t, which I know is 1 second, right? So I'm going to get out my handy dandy phone calculator. Actually, I have a, I don't know if you can see this on the camera here. I've got my HP calculator emulator on my phone. But I'm going to use that D naught A, that's 7 degrees Celsius. Then I'm going to get my exponential function. I'm going to calculate this real quick and see what we get. I get dA of 4.2457 something degrees C, about 4.2. This would mean that now the temperature of thing A would be the room temperature plus 4.2, so 27.2, right? Just plugging it back in, solving for temperature in that temperature difference formula. So let me change colors here and we'll look at thing B. Temperature difference, that's of 1 at 1 second. D, let me write down that 1 second of t equals 1 second. dB naught e to the minus kt with t equal to 1 second. So that's 17 and the same exponential function, right? I get a temperature difference of 10.31102 something degrees C, which tells me that after 1 second, the temperature of B is 10 degrees, so 33.3 or so degrees C. So yeah, temperature B, object B, cup of water B, still hotter, right? I ran a little bit long on this. We're going to stop here after this example of Newton's law of cooling, and we'll come back and talk more thermodynamics in the next video.